Welcome back to Learning Solidity. Now in today's tutorial we'll be covering instructional assembly. In our previous tutorial we covered functional assembly. Now the only key difference between the two sets of assembly is that functional assembly is a lot easier to read. There is no extra functionality for using either. Possibly the only benefit of using instructional assembly is that it makes it easier for you to understand what's going on in the debugger when you're stepping through code. And that's kind of one of the key reasons I'm doing this tutorial. Personally, I would discourage the use of instructional assembly unless you really want to. And even then, I would still discourage it. What I'm going to do for today's tutorial is I'm essentially going to take the very first example I took in the previous tutorial when we were looking at functional assembly, and that is the concept of creating a loop. Now we're going to do the same thing for the instructional assembly. The only difference is that we're actually going to first try and understand what's going on behind the scenes of one of these functions, because that is how we're going to get going with writing our assembly. Now the key thing when you're actually creating instructional assembly is understanding how the stack works. Obviously memory is important, but for this concept we are literally going to keep it as loose as just looking at the stack. Okay, so what I'm going to do is I've already got some code here from the previous tutorial. I've removed the rest of the functions because I'm not going to replicate them, because like I said, I'm trying to keep this as lightweight as possible, because I don't feel that many people are going to really want to start writing inline assembly. So first let's create our assembly contract, and what we're going to do is we're going to step through one of the previous created functions. So I'm going to use asm loops because that should be the most simplistic. So let's jump into the debugger. Now the only two tabs that we need open for this is instructions and stack. Okay, so let's just step into this. Right. So when you actually first interact with a function in assembly, pardon me, you're going to execute a couple of predefined, or push a couple of predefined things to your stack. Now these are going to be things such as the function call itself and any other operations or so forth that's going to be involved in that. Now what essentially is going to happen first with this is it will assign any parameters or any return variables and add these to the stack. Now the first thing that we're actually going to see when we kind of step over this is the addition of the _r uint to the stack. Now you're looking at this instructions here on the right hand side where you're seeing push 100. Now that is not actually reference to this, if I'm correct. That's actually reference to the next constant we're going to look at. So if I actually step over this, it will have added the value 00 to the actual stack itself. The only thing that I could potentially think of that could be is it could be adding the 00 for the _r uint, and that is actually part of the optimization of the Solidity code to actually do that. And then it's identifying that that is also 0, so it's matching the two values, being one the variable _r and one the constant 0, and then basically duplicating the value, which is essentially what dup1 is, and then that will essentially add the value of whatever's currently at the top of the stack again to the top of the stack again. So what I mean by that is when we step over the dup1, we now have two values of 0 in our stack. Now what it's going to do next is then jump to a destination, which is then part of our loop. Now this let I, which is not actually available to inline assembly, is more of a pointer to a position in the stack. So when you actually create a value using let I, all it's doing is assigning it to the stack and then using that as a pointer to the position in the stack. So when it's executing methods such as duplicate or swap, it knows the position in the stack of what you're actually duplicating or swapping. I hope I'm explaining this well enough, because it's actually quite a complicated thing to explain as well as get your head around. But I'm hoping when I actually start writing the inline assembly or instructional assembly, it will start becoming a little bit clearer. So the next thing we're doing is jump into a destination after assigning the constant I, the constant 0 to the stack, as well as the variable r, which is a uint, so that's also going to be 0 into the stack. So this is going to be r. It kind of works obviously like a stack, hence the name stack. So as you keep adding values, the lower values will keep going, or the first access values will keep going lower and lower in the position of the actual stack. So if I now step over into the jump destination, which is essentially jump into a specific point or specific label, we were then going to start looking at this add method, or this add instruction. Now the first thing it's doing is pushing 1 into the stack. Now the reason it's pushing 1 into the stack is because we have referenced the constant 1. The next thing we're doing is duplicating the constant I. So what that's essentially doing is, because we're referencing I, we need to actually use that for our add instruction. So when you're using any sort of like add, subtract, multiplication, equivalency, any comparator, anything like that, it will use the first and second place. So for instance, if an instruction takes 2 parameters, it will take the first place of the stack and then the second place of the stack. Because we are adding 1 to I, we are first getting the last value. You'll see it's a reversed order of how you basically would write functional assembly. So the 1 comes first, which gets pushed in first, then the I gets pushed in, which, because I is a reference to the pointer in the stack, it's the second position of the stack, which is actually here. Because we're pushing 1 in, obviously the I value gets pushed down the stack, which then becomes the second place, as you'll see when I actually step over. So 1 is currently in the first position. Our reference to I is now in the second position. We need to duplicate the second position, which is now 0. So then we're applying the add operation, which is going to add the first and second positions in the stack together, which will return 1. So what will happen is, when you execute that, it will remove those 2 values of the stack and then combine them together. Then what we're doing is we're swapping that with the I reference again. So we're swapping I with 1, or essentially the top position of the stack. Now those 2 values have been swapped over, we no longer need 0 because it was the old version of I, so we're now removing that from the stack. We're essentially then doing the same thing with the return value. The only difference with the return value, because it got added before I, is that it's now 1 level lower. So I was manipulated using duplicate 2, and the return value is getting is now pushed down, so therefore it's duplicating the value, or the stack position of 3. Again, if that makes any sense. Like I said, this is always hard to explain because it can be quite complicated. So again, it's doing the same thing, duplicating it, adding the 2 values, then swapping the second position in the stack, and that value 1 should appear essentially down here, 0 should appear up here, like so, and then that value is going to get popped out. And now it's pushing the value of 10 into the stack. Now, the reason it's pushing the value 10 in, this is where the instruction set now gets quite a little bit more complicated. You're seeing 0A, but that's actually the hexadecimal value of 10. So what will happen now is that 0A, or 10, will get pushed to the top of the stack. Because, like I say, it's doing from essentially right to left, it does the right operation first. So that's going to first get 10, duplicate 2 because it's the pointer to I, which is 1, do a less than comparison. So we're essentially saying, is 1 less than 10? It's not. So we're there returning, sorry, is 1 less than 10, which it is, which is then returning 1. We're pushing the value 96, sorry, which is actually the reference to this this loop label. Because that passed, we are essentially now jumping to the loop position, which is now, we're basically saying go to this position. We're popping the value and jump into the destination. So we're going to do that over and over again, obviously 10 times until we have reached the value 10, where this less than then fails, and then we'll break out, and essentially the return will return as the value of 10. Now, I may have not explained that overly well, but let's just jump in straight away to the instructional assembly, and hopefully you'll be able to see this a little bit better. So, as before, we have inline asm loops, public returns uint underscore r, and we need an assembly block. So the first thing that we need to do is define 0. Now, as you saw before, anytime we referenced a constant value, it appeared in the stack. So let's do the same thing. 0. Okay, now 0 should be in our stack. So we already have the first position of the stack here. Second position of the stack is now here. Let's actually bump this up because we need a comparison to obviously equal to 10 as well. So I'm going to create a little bit of a constant here and add 10 to the stack too. So now the first position of the stack is 10, second position is 0, and third position is underscore r. Okay, so we've got that out of the way. The next thing we're going to do now is create our label. So again, same sort of syntax because it's a label. Now the next thing we're going to do is we are going to do our addition. Now, if you remember what I said, this is the first position of the stack. That is currently the second position of the stack. So what we need to do is we need to duplicate 2, which is the second position of the stack, add 1, which will then get pushed to the top of the stack. You could also do push as well, but I'm going to just leave it quite clean and simple for now. Then we're going to do an add. If you remember me previously stating, when you do an add or less than or greater to or whatever, or any conditional or manipulation, whatever amount of parameters it is, it will take the X amount of parameters from the top of the stack descending, or ascending should I say, sorry. So it will take 1, which is at the first position of the stack. We've duplicated 2, which is I, and it is now at the second position of the stack. And now we're adding those two values together. Now we need to basically assign this value to essentially what was the original I. So let's just write, I'm going to write some comments in this to make it a little bit clearer. So this is I, we'll call this max, and what we're essentially doing with this method, as previously before, is I colon equals add I1. So as we're calling add, we've now added those two values together. Now this add should have added those two to the top of the stack. So 0 and 1 is now 1 and it's at the top of the stack, but we need to swap it out to this value here. Because it adds the two values together, it removes the value at the top and makes the second value the top of the stack. Again, this is where it really gets complicated. So what we need to do, because our new add has basically combined the values and made that then the top of the stack, we need to then return, or I say return, we need to then assign it to what would be at position I. So we do that by simply swapping 2. And now this should basically swap the value of add with what was the value of I. Now to actually also make that a little bit easier as well, we're going to now remove the swapped value with pop, and now we're going to do the same thing with the return. Because the return was at the third position of the stack, we need to do the same sort of thing. So let's say do 3. So this time it's r colon equals add underscore r1. So we're adding 1 again. We're adding them together, we're swapping them with the position 3 of the stack, we're then popping the value because we no longer need the old value of what was underscore r, and we are then now coming to our comparison, which I'll leave I'll move the comments above those so it's a bit clearer. So the next thing we're going to do, as you can see here, is the jump to I. Now there's a couple of bits that we need to break down first. So we're going to first break it down by doing the less than. Okay. So what we're doing is checking if 1, or what is I in the stack, is less than 10. So because we need to do this in reverse order, 10 needs to come first. So let's duplicate the value of 1, which if you remember rightly should be the current first value of the stack. Then because we've actually then duplicated that value, the second value in the stack now becomes the third value. We then need to duplicate 3. Then we need to execute the comparison of less than. Then because we are doing the let's miss the function here. We're doing the jump less than. So like I was stating, it becomes in reverse order. So the 10 first, which is there, the I first, which is there, the less than, which is there. The next thing we need to state is the loop. So we're going to go to the label loop. Then we're simply saying jump I. So it should use that as the second parameter, that as the first parameter, and jump if it needs to. And finally, what we need to do, because we've matched that condition, is simply pop these two values, because at the end of the stack we don't essentially need them. You don't have to pop them. I just think for sort of housekeeping it's always good to. So let's pop that, and let's pop that. So that should be clean. Now if I've written this right, which I hope I have, let's start by cleaning this up, create a function, clear it. So let's just do a test. So our native loops returns 10. Let's also have a quick look at the gas. So again, gas is 999 for the native loop. Our ASM loop details returns 10 and has a gas cost of 702. Our inline ASM loops, let's have a look, returns 10, gas cost 685. We've only made a minuscule improvement on the gas cost, but we have the correct value being returned. Thank God. I hate honestly, when you're doing instructional assembly, you learn that it can get really complicated. This was the biggest thing that caught me out when I was writing this, because I was like, I'm pretty sure that I should be duplicating the second value because the second value is that, and then I wasn't realizing when I was actually duplicating the first value, it was pushing the second value to the third value. And like I say, this is where instructional assembly can get really complicated. So let's just actually execute our inline ASM loops, and let's just debug it just to make sure that it's doing what we think it's doing. So bring up the stack, bring up the instructions. Okay, so as you can see here, similar to before, it's done a little bit of optimization. Because R was already assigned to 0, it's already seen that 0 is matching something else in the stack, and this is what I'm assuming that the compiler has done. So it's also just duplicating 1, so the same value essentially exists in the stack. It's then pushing 10 to the stack. So okay, so now we're sort of like have our little reference point set up here. So this is the first point in the stack, this is the second point, which is what we assume is I, and then this is the third point, which is what our return value is. So we're first incrementing I, which is what we think the second point in the stack is. So again, we're duplicating it. So the first thing that will happen is duplicate the second point in the stack, which will then become the first point in the stack. We are then adding the value 1, which will then force the first value in the stack to the second value, and this value 1 will be the first value in the stack. We're then executing the add instruction, which will then take the first and second value, combine them together into a single value, and get rid of any excess value, which is now 1. We are now swapping the value of 1, or the first position of the stack, with the second position, which is then becoming here, because when you do that, it kind of sorry, it kind of assumes that this is now, because it's a temporary value, this is now the second value and not the third. So if you step over that, it then switches those two values. We are then popping our new top value out. We are then doing the same for the third value, which is down here, so you'll see that happen again. So 1 gets added, 0 gets added because it's duplicating the third position with 0. Then 1 gets added, adds them together, which is 1, swaps the two positions, so position 3 and 0 here will swap, pops the value of position 0, or what would be position 1. Then it loads in the first value in the stack, which is be 10. Then it loads in the third value in the stack. Because we've loaded in the first value, if you see what I mean now, it pushes everything down 1. When you call a duplicate or swap, it actually increments the position of the stack. When you call something like a comparator or so forth, it doesn't actually increment the position of the stack. Again, this is where the complication comes with the instructional assembly. Then you can see the comparison of those two is equal to 1, because 1 is less than 10. Oh, sorry, no, that still hasn't executed yet because the 2 values in the stack are still there. That should return 1, which it has done. Then we're basically saying go to loop if the jump case has been matched, which it has done. So this is actually just reference to the jump of loop. So we're basically just saying go to this point in the actual code, which I think is just a reference to the actual instruction here. It's going back to the loop, and then we'll do the same thing over again. Obviously this time instead of 1 we're incrementing to 2, then you should see it again to 3, obviously then 4, 5, and so forth. I'm not going to say I can just basically copy, just go to this final point in the stack. I could just drag this along. So there we have it. We should see values of A appearing everywhere. So that's 9, A, and A. Obviously this is the point now where it'll no longer match because 10 is not less than 10. So it returns 0. Doesn't matter about the loop label because it's not going to match. The jump I has not been matched. We no longer need either of these 2 values of 10 because we only need the return statement. So pop, pop. We have the return value, and then we're simply returning it. And that is the end of the instructional assembly loop. I hope this has been relatively easy to digest and follow. It's not so straightforward to sort of explain. I'm not the greatest at explaining sort of instructional assembly. I hope I've conveyed this as best I could. Either way, if you did find this useful, give it a thumbs up. I know some people are probably just sitting there saying, what the hell did you just say? If you want me to break this down in a more simpler context, feel free to leave a comment down below, and I can do another tutorial on this when I use a much more simpler context to sort of try and convey this with, because I know obviously in this context the loop is probably not the most straightforward. But obviously any feedback is much appreciated, constructive or not. Actually, in some cases, if it's toxic, feel free not to. If you want to keep up to date with my latest videos, obviously I'm going to be covering as many topics as I can with Solidity. I've already done a sort of a wide variety. I will keep going, and obviously if you're interested in that, hit the subscribe button. But for now, good luck with writing Solidity, and I'll catch you next time.